Hi, chem students. Let's look at a problem that you commonly see in acid-base chemistry. One where you put an acid or a base into water and look to measure the pH, and from that discover what the equilibrium constant is. So the key to doing one of these problems is just to realize that the pH is another way of saying here's what the system is like at equilibrium. So we'll give you an initial concentration, something you can create in the lab, and then you can go measure in the lab this equilibrium constant or this pH, and from that get this constant, which is useful for everyone else who wants to study this system. So here's an example: 0.321 molar solution of some substance NX3. I'm hoping when you saw that you initially said, hey, that's a base because it's got this nitrogen attached to three things, and then you look at it and it says, oh, I've made this solution and it's created a pH of 9.79. Well, that's a basic solution because the pH is greater than 7. And, so now you're being asked, what's the equilibrium constant? To begin a problem in equilibrium, you want to write the ice table out. So let's go ahead and do that, which requires us to create the reaction. So NX3 is a base. It's an aqueous solution. So we're going to allow it to react with water, which is a liquid in this case. And after that, we know that this base is going to have these electrons available to either accept a proton, or in other words, to donate these electrons to the water, which is the acid, and create the new bond between the proton and the NX3. So we're going to get this weird NHX3 plus aqueous stuff, whatever it is. And then we'll be left with OH minus. So there's our reaction. What's the initial concentration? Well, it's 0.321. This is a liquid, so we don't care. So we just put a little line there to remind ourselves not to do anything with it. Initially, we imagine that there's none of this stuff in there. We didn't put any in. Therefore, we're going to say there's 0. So when we look at this, the change is going to have to be dictated by thinking, well, heck, the Q is equal to 0. And no matter what the K is, Q is less than K, because 0 is less than whatever the equilibrium constant. So we're going to have to shift to the right. There's no way you can shift to the left anyways, because there's no NX3 and NHX3 plus to react. There's no OH minus to react. So we're going to shift to the right. That means we're going to get a minus X here. Who cares? It's this water that's a liquid, and a plus X and a plus X. So when we're all said and done, when we reach equilibrium, it's 0.321 minus X. Who knows? Who cares? X and X. And you might be thinking, well, heck, we have no way to solve this, because to solve for X, we would likely need to have some more information. Well, we do have more information. We have the pH. So our goals define K, but we have this pH thing. Well, let's think about the pH. At room temperature, the pH plus the POH is equal to 14. That means I know for sure that the POH for this system is equal to 14 minus 9.79. And that's equal to 4.21. So I know what the POH is, but there's one more thing that I know. I know that the OH minus concentration at equilibrium can be found by doing 10 to the minus POH. So 10 to the minus 4.21 will give me my OH minus concentration. If I do this math, I get 6.166 times 10 to the minus 5th molar. You might be thinking, what good is that? Well, here's the good of that. My OH minus is right here. Oops. My OH minus is right here. So X is equal to my OH minus concentration. Therefore, if I create my equilibrium expression in terms of X, I can plug in what I know its value to be, which is 6.166 times 10 to the minus 5th. Let's go ahead and do that. So my equilibrium expression, K sub B, is equal to my NHX3 plus times my OH minus divided by my initial concentration or my concentration of N, not NH, but NX3. All of these when they're at equilibrium. And in terms of above, that's equal to x squared over 0.321 minus x. But I know what x is. This is x. So I can just substitute that in. There's no need to do this simplification where we assume there's a small x. We don't want to do that. We're not trying to avoid doing the quadratic here. So go ahead and plug it in. So I get 6.166 times 10 to the minus fifth. I got to square that. Don't forget to square it. Divided by 0.321 less that same value of 6.166 times 10 to the minus fifth. If I do that math, I get 1.18 times 10 to the minus eighth, or, since I really only have two significant digits, 1.2 times 10 to the minus eighth. And that's my equilibrium constant. So follow this plan. When you have a pH, you need to think about a pH as it's giving you information about a concentration at equilibrium. If it's a base, you can find out what the pOH is. If it's an acid, you already know what the pH is. And those connect to the species that are being produced in the acid-base dissociation with water. So there you have it.